another statistical topic. Before I get started today, I actually gonna make some announcements. Of course, the midterm two has already been reading, and you know we are in the process of grading the exam, and I deliberately delay the posting of assignment six. Assignment six is going to be the last assignment of the semester because I want to slow down. I want to slow down and enable you to actually tidy up, for those of you who have missed one or two assignments before. So you can probably consult, with me so that you can, if you want to request for makeup, okay? Because I know some of you did not join on time. So the last assignment is going to be posted tomorrow, but it's not going to be due the following Sunday, okay? Because it's going to be the last assignment. Go ahead. Yeah. Okay. I also want to tell you that according to the syllabus, I propose having six assignments in the semester, and I'm only going to use five. The lowest, the assignment with the lowest grade will be dropped. So if you are satisfied with five assignments so far, you may decide only, to opt out of assignment six. Does that make sense? You may decide not to complete assignment six if you are satisfied with the five that you've done so far. Okay, I want to go into, this topic is the remainder of chapter five, because tomorrow we're starting chapter six, which is going to be the last chapter of the semester. But this is going to be the last part of chapter five that I actually call multivariate, you know, joint distributions. Of course, in the outline, I'm actually going to talk about multinomial distribution. Of course, we've started multivariate distribution. We look at the example in a continuous random variable. I walk you through the joint normal density. Okay, what I'm going to talk about today, the multinomial, is can we have a way to have a multivariate situation in a discrete case? Can we have a way to extend a binomial distribution in a situation where we're no longer interested in just a single measurement? I'm going to walk you through that today. I'm also going to walk you through what I call the expectation of a product. We've been working with the expectation of linear combination. Okay, but right now, in a situation where we want to figure out the expectation of the product of random variable. And why do we need the expectation of a product of random variable? Is because we need the idea of expectation of products in getting covariance and getting correlation. I'm going to say that again. We don't just do what we do. There's a reason why we do what we do. We're going to be focusing on expectation of product because we know before I can obtain the covariance and correlation, then I need the idea of the expectation of a product. Okay, I'm going to walk you through all this today. In statistical analysis, of course, we at times we find ourselves in a situation where we basically want to see, we observe two variables, right, at a time, and we realize that they changes together, okay, which means they varies jointly. Okay, if I want to look at the way they are connected, of course, basically going to look at correlation. But if I want to see the way, they varies together, where what I'm interested in is just the direction of the relationship, then I'm going to be talking about covariance. But if I want to talk about both the direction of the relationship and the magnitude of the relationship, then I need a correlation. So the correlation is performing two roles. I'm going to say that again. Covariance perform one role, while correlation two roles. The role in the role of the covariance is just to tell us the direction of the relationship between two variables. Covariance cannot tell us the magnitude, cannot tell us the strength of the relationship. We have what we call the strength and direction. What tell us both is correlation. Correlation tell us both. Okay? Correlation tell us, say measures of, going to tell us the direction and the strength of the relationship. Okay? But the covariance is only going to tell us, the direction only. It can tell us the strength. And therefore, when I standardize covariance, we got correlation. So we want to look at that today. Now, but let's first go into multinomial. Now, let me tell you this. The other time when I was working you through binomial distribution on that discrete type, we use binomial distribution to figure out the probability of a discrete random variable with two possible outcomes. That is why it's called binomial. An example is when I have a coin, a fair coin, right? There are two possible sides, right? Okay, so if I flip that and I'm interested in the side that will show up, I'm going to apply binomial distribution. But what if in a situation where we got more than two possible outcomes? An example is when you talk about a balanced die. How many sides? 1, 2, 3, 4, 5, 6, right? There are more than two possible outcomes. Okay, more than two possible outcomes. Okay, therefore, when I perform experiment 10 times with a die, and I basically want to see the number that comes up, then I'm performing a multinomial experiment. I'm performing a multinomial experiment because there are more than two possible outcomes. Now, this is the statistical architecture of a multinomial distribution. Okay, like I said, the outcome is E1, E2 up to EK. Here we got K possible outcome. And of course, we got probability associated with each of these outcomes. For E1, the probability of E1 occurring is P1. The probability of E2 occurring is P2 all the way to PK. Now, if you take a look at a lowercase n that you see now, is basically the numbers of trials. And if you take a look at what you're seeing right now, give me 1 second. I'm actually going to use my pen. If you look at this guy here, what is he telling us? It's more or less like we partition the numbers of trial, okay, into different kinds, of outcome, x1 up to xk, and each outcome has its own probability. Okay, what is that? What is that guy telling me? Okay, p1 raised to power x1. It means for every outcome there exists its probability. Okay, so the outcome x1, the probability of x1 occurring is p1, and that's why you see p1 carrying s1 in such a way that when I sum all the outcomes together, summation xi, if I have k outcome, that is basically going to be n. And don't forget, when I sum the probability together, I'm actually going to have from P1 to PK, that is going to be 1. I present to you what I call the multinomial. Okay, this is what we call the multinomial probability distribution. The multinomial probability distribution is an example of a multivariate distribution. This is actually falling under the discrete type. Okay. Now, if I want to make it another way to rewrite the distribution now is to write it this way. Take a look at this. It's another way. Suppose that we observe an experiment that has a possible outcome. Okay, the possible outcome I go from O1 to OK. Okay, independently n times. Okay, and P1 is the probability of O1 occurring, P2 probability of O2 occurring, up to Pk, the probability of OK occurring. Then the joint probability function of the random variable can also be written as that. Okay, that is what we call the multinomial. Those of you online, can you say confirm again if you are hearing me clearly? Is everyone hearing me clearly?
Yes, we can hear you.
Okay, thank you so much. Thank you for confirming that. Okay, now the next thing I want to walk you through now, how do we derive this statistical architecture? This is how we derive that. And I need you to pay attention now. Okay. You know, when you take a look at the first one here, give me 1 second. When you take a look at this guy here, you know, x1, the outcome x1 is basically going to come from the total numbers of trial. Okay. And when you go to the next one, if I want to talk about n x2, okay, I have to put into consideration the numbers of trial is no longer the same. You have to subtract the event x1. Does that make sense? That's what you see. N minus x1, x2. If I get to x3, take a look at that. When I get to x3, okay, I have to update my numbers of trial. That, of course, I have to subtract the x1 and x2. There's something is going to continue to go that way. Okay, when you go that way, okay, when you go that way, you basically going to see if I want to write this another way to write that in a combinatorial way. Okay, of course, when I have n factorial, okay, when I have n, you know, combinate, when I have this guy, it is same thing as n factorial, r factorial, n minus r factorial. Okay, so you can say that is written that way, and the same way I can also, write this to go this way, and also write this guy this way, and that will continue to go that way. Take a look at that. Okay, and when I have that, okay, at the end of the day, I'm actually going to find myself in a situation of that, where I'm going to have a multinomial. What I'm just giving you here is just to show you how the multinomial distribution is actually derived. Okay, now what I want us to do now, can we have an example of multinomial distribution? Let's take a look at the example right now. The complexity of arrivals and departures of planes at an airport is such that the computer simulation is often used to model the ID conditions. For a certain airport with 3 runways, it is known that in the ID setting, the following are probability that individual runways are accessed by a randomly arriving commercial jet. Okay, how many runways? The fact that you have 3 runways, okay, the idea of multinomial is going to work because you have more than 2 runways. Okay, because the fact that you know you know we may want to figure out how the probability a particular runway will be busy. Now take a look at this from uh history. We have this data. The probability that the runway 1 will be busy is 2/9. The probability that runway 2 will be busy is 1/6, and the probability of runway 3 is that would be 11/18. Take a look at that. Here now we're talking about the probability that individual runways will be accessed. Now we need to talk about the outcome in a given situation. Now, don't forget, in multinomial, we normally say we have x1 outcome, x2 outcome. This time around, our x1 outcome is basically going to be the numbers of planes arriving. Okay. Now the question asks, what is the probability that 6 randomly arriving airplanes are distributed in the following version? Okay. Runway 1, 2 airplanes. Runway 2, 1 airplane, and runway 3, 3 airplanes. Okay. What is n? The total numbers of airplane we're talking about is 6. Okay. Now, do you know that the idea of multinomial probability distribution can actually be used here? Okay, you can say I wrote 2, 1, 3 because if I basically want to, if I basically, okay, let me do this. If I basically want to use that, I'm actually going to write f of I'm going to write f of x1, okay, comma, f of x2, okay, comma, f of x3, okay. Then after that, I'm actually going to write the p1, okay, the p2, okay, the p3, the p3, and n. So this is going to be equal to the multinomial. Okay, so here now it's like I'm defining my characteristics of interest. Okay, of what is my P, what is my X1, my X2, my X3, my P1, my P2, my P3, and the sample size. Okay, and what I've done now, I've plugged that in, I plug all of that in, and I compute that. Okay, now the probability that 6 randomly arriving airplanes, okay, are distributed in such a way that 2 airplane is going to go to runway 1, and 1 airplane is going to go to runway 2, and 3 airplanes going to go to runway 3. That probability is 0.1127. So which means that occur 11.27% of the time. Does that make sense? That is how multinomial is actually being used. Okay. Um, Before I go into something else, I want to give you another example. I'm going to stop my share now. I'm going to stop my share now, and of course, I need those of you online to focus on the board. Okay, under the multivariate situation, I've walked you through multivariate normal. I remember we focus on bivariate normal, 2 variables, okay, in the continuous side. I've also walked you through the multinomial now, which is a multivariate version of a discrete type probability distribution. We also have a multivariate version of order distribution as well. But I'm going to give you this example, and I need you to focus on the board. Okay, we are actually counting down to the final exam, right? Okay, I need you to pay attention. For instance, if you're given, the other time I said if x follow days with parameter days, you remember that's an exponential, right? F of x is 1 over beta exponential raised to power x over beta, x greater than that and this greater than that. Do you know I can rewrite this exponential in another way? I can also have this x follow exponential with parameter alpha 1. I can write f of x to be equal to alpha 1 exponential raised to power alpha 1x. And where x greater than 0, this is another version of exponential. Please take note. This is an exponential. This is another exponential. Okay. if you take a look at what is happening here, 1 over beta is more or less alpha 1. Does that make sense? Now, this is not where I'm going. I want to consider a bivariate exponential. Bivariate exponential. Okay, I want to consider bivariate exponential. Okay, now, if they gave you something like this, f of xy, this is a distribution function. Okay, this is a distribution function. These are an uppercase, right? Okay, equal exponential raised to power alpha 1x plus alpha 2y plus theta xy. Look, and then you are told that alpha 1 greater than 0, alpha 2 greater than 0, and theta greater than 0, your x greater than 0 and y greater than 0. Now this, if you are given this, this is a distribution function. This is CDF, right? A CDF of a bivariate exponential, and maybe they ask you to figure this out. Number one, what is this? Okay, what is the joint? This one means the joint PDF, right? The joint probability density function. Okay, what I've walked you through in this class, I walk you through a CDF for univariate, right? You know how to figure out the PDF from the CDF. All what you're going to do is to differentiate, right? What if in a situation where you got a bivariate like this, and from this guy, they want you to get this guy. Not only that, they also want you to get this guy. They also want you to get this guy. And not only that, they also want you to get this guy and this guy. Oh my God. Take a look at what I have now. You take a look at, from just this guy, we want to get all of this. Okay. We want to get all of this from that guy. What are we going to do? Okay. I need you to pay attention now. Okay, I need you to pay attention into what you're going to do. Okay, you remember when when you have a univariate where you have a CDF. Okay, if you want to get a PDF, what do you always do? You're gonna do DDX of this guy, right? You're going to do DDS of that guy, right? If you have a CDF, this is CDF. I'm talking about univariate case, right? And you want to get the PDF, right? Okay, so you're going to differentiate the CDF. Okay, now right now, what are you going to do here? So what I'm trying to say, if you want to answer question number 1 here, okay, if you want to answer question number 1, okay, f of xy, oh my God, it's going to be d squared, okay, the x, the y. Oh, do you see that? The square, the x, the y. You can also rewrite that as this, the y, the x. Okay, take a look at that. It doesn't really matter if you differentiate with respect to x force or differentiate with respect to y force. It doesn't matter. So what I'm trying to say now, okay, you actually going to have, you can do ddx, okay, ddx, okay, into d the y, okay, into d the y of this guy, alpha 1x plus alpha 2y theta xy. Take a look at that. That's exactly what you're going to do. Okay, now when you first differentiate with respect to y, then you're going to continue to differentiate with respect to x. Whatever you get is basically going to be your PDF. And don't forget, the moment you get your PDF, oh my God, f of s can be derived. That's a marginal, right? Where you basically need this guy. And you're going to use the range of that, from 0 to infinity. Take a look at that. Oh my God, if the moment this guy is wrong, automatically this guy is going to be wrong. Be careful. Okay, and you want to get the f of y. F of y is going to be easy now. Okay, you got f of x y dx, right? Okay, you can try that. And you know what? The moment you get the marginal, like I said, these guys are marginal, right? Okay, if you want to get this guy and this guy now, they're going to be easy, right? Okay, they're going to be easy in a way. Okay, they're basically going to be easy in a way because take a look at if you want to get that now, the conditioner. The conditioner is going to be f of x given y is going to be f of xy divided by f of y, and of course f of y given s is going to be equal to this divided by f of x. Please take notes. You can see everything starts from here. Okay, any question? Any question before I continue with the slide? So watch out for stuff like this. Okay, watch out. Okay, like I said, revise your knowledge of calculus because that is actually needed. Actually needed. Okay, give me 1 second. I'm going to share my whiteboard again. But the lecture slide again. Those of you online, can you see confirm? If you can still hear me clearly, is everyone still hearing me clearly? Thank you so much. Thank you for confirming that. Okay, so why no lecture slide? Can somebody online again confirm if you can see my lecture slide?
Yep.
Can somebody online confirm if you can see my
Yes,
lectures?
we're
Okay,
able to
thank you
see
so
them.
much. Okay, thank you so much.
Mhm.
Now I want to go into the expectation of the products. I told you why we need the expectation. You're going to see the reason now why we need the expectation of the products. Now, I present to you expectation of the product for both discrete and continuous case. For discrete case, okay, if you take a look at what you're seeing now, this is more or less like expected value of a g, a function of x and y. Okay, let's say I'm not talking about product now. I'm talking about function of x and y. Okay, and I want to figure out the expectation of that. Because I got two variables, of course, I'm actually going to have two summation. Okay, because x and y are discrete. And for if x and y are continuous, I'm actually going to have that guy, I'm having two integrals. Now, walking you through, I want to walk you through the discrete case. Now, you remember the other time, right? I actually presented to you what I call a contingency table, where we got levels of x and the levels of y. Of course, x and y are discrete. Oh my God, you're given that. I told you the other time. Uh, you got a marginals there, right? For y and for x, the range, the levels of x and y in these situations are the same. Okay, they each of them got three levels, right? 0, 1, 2. Now, how do I find the expectation of a product? Look at that expectation of xy. Okay, I'm gonna make use of my pen now so that you're gonna see what I'm talking about. Okay, that is what we call. Do you see what I circled? That is the expectation of the product of x and y. Okay, now we're talking about discrete case, making use of the table now. It's basically going to be summation, xy, and the joint. You're going to make use of the joint. Okay, now making use of the joint. Oh my God, I'm actually gonna have how many possibility? How many cells do I got? I got 6 cells, right? Sorry, 9. 3 by 3. 3 levels of x, 3 levels of y. The very first one I'm gonna have is 0, 0. When x equal to 0, y equal to 0, then what is the probability associated with that? That would be 3 over 28, right? That's gonna be 3 over 28. Okay, when x equal to 0, y equal to 0, 3 over 28. When x equal to 1, okay, y equal to 0, 9 over 28, and go and so on like that. Okay, if you take a look at my formula here, oh my God, that's exactly what I'm actually using. And finally, I'm basically going to end up in getting that what I got. Is there anyone, either in person or online, who doesn't understand how I figure out the expected value of the product to be 3 over 14? Is there anyone, either in person or online? Okay, now the silent actually implies you understand how I figured that out. Then I'm going to go to the next slide. Now, of course, I've walked you through this guy before. If a function of two variables x and y is equal to x, and that one equal to y, of course, you know linearity of expectation. Okay, expected value into x plus y can be the same as expected value of x plus expected value of y, and expected value of x of expected value into x minus y basically going to be expected value of x minus expected value of y. If you really want to understand this, let us apply now. If x represents daily production of some item from machine A, and y the daily production of the same kind of item from machine B, oh my God, you got two different machines in your company producing the same item. This is machine A. This is a machine B. They produce they produce the same items. At times, you may basically want to know what is the totality of what is produced. Maybe what is the average of the addition. That would be expectation into x plus y. And at times, you may want to look at the difference between the two machines in terms of production, in terms of what they produce. That would be what? Expectation into x minus y. Depending on whatever you want to you want to, and that was why I said x plus y represent the total number of items produced by both machines. At the same time, I can also figure out the difference between the two machines. Maybe I basically want to compare the efficiency of the two machines, which one produce more items better. Okay, now I want to tell you again, the expectation of the product can be equal to the products of the unconditional means. You remember what conditional mean? The unconditional mean is the expectation of x, expectation of y. We're multiplying them. But do you know condition under which expectation of the product can be written that way is when x and y are independent. When x and y are independent, it's more or less like we are using the idea of a joint probability here. The probability of A intersection B, when A and B are independent, what happen? You're basically going to multiply the respective probability. That's all. So expectation of the product is the same thing as the expectation of that. Take a look at that. And let me tell you, in a continuous, let's say x and y is a continuous and random variable. They have a joint distribution, f of xy. How do I figure out the expectation of the product? Please take note. If you want to figure out the expectation of the product, you need double integrals. How many variables involve x and y? So it's going to be integral xy f of x comma y the s the y. Please take notes. Okay, so that is exactly what I mean here. That's what I mean here, right? Okay, and I say that the moment x and y are independent, we write that as what you see in here. Okay, give me 1 second. I'm going to make use of my pen now. We can rewrite that as what you see in here. They can be separated if they are independent. That's what I mean. Okay, that's the integral that can be separated. The only condition on that way they can be separated is when x and y are independent. But if they are not independent, of course, they cannot be separated. Okay, now I want us to go into an example now. Okay, it is known that the ratio of gallium to arsenide does not affect the functioning of gallium arsenide wafers, which are the main components of microchips. Let X denote the ratio of gallium to arsenide, and Y denote the functional wafer retrieved during a 1 hour period. X and Y are independent. Pay attention. Now they are telling you now X and Y are independent random variable with this joint function. Situation where X and Y are independent, let me tell you, if X and Y are independent, okay, there's a lot of implication. There's a lot of implication. If X and Y are independent, the implication f of xy can be written as this. Okay, f of xy can be written as that. Not only that, when you find the expectation of a product, it can be written as this. Not only that, the f of s given this is going to be f of x. Not only that, the f of y given this is going to be f of y. Please take note. Okay, and not only that, the variance of y given s is going to be equal to the variance of y. The variance of x given y is equal to the variance of x. This occurs in a situation where x and y are independent. There's so many situations. Okay, now you're given this now, f of xy equal to that, and you're told, okay, you can see the state space of x and the state space of y. Okay, now take a look at this. I want to find the expectation of a product. Because I've been told that x and y are independent, you know what I'm going to do? I'm basically going to say, okay, if I want to get expectation of a product, do you know I can just get the expectation of x and expectation of y, then multiply them. Okay, now when I want to get the expectation of x, I go 4/3, expectation of y, I got that. Okay, and when I did the expectation of the product, that give me 5/6. Now let us now check. When I multiply expectation of x by expectation of that, it give me the same 5/6. You can investigate what you're seeing on the board. So when you try what you're seeing on the board, okay, you're basically going to have what I said. Okay, you're going to have, and don't forget, if you want to find the expectation of x, don't forget you're going to use this. If you want to find the expectation of y, you're basically going to use this. Don't forget. And before you can use it, you need f of x. You need f of y, and you know your f of x to be f of x y the y, and you know your f of y to be f of x y the x. Okay, and of course the range of x is from 0 to 2, so 0 to 2, and the range of y from 0 to 1, 0 to 1. Okay, so 0 to 1, 0 to 2. You can verify all of that. Okay, so take a look at what I just said now. Okay, if you derive that, you're going to see that that is going to be equal. Now, another generalization that I want to go is if x and y are independent now. Okay, the variance of the linear combination is going to be that. I think I walked you through this guy before. Okay, if x and y are independent, that's what you're going to have. Okay, now I want to quickly move to generalization. This is generalization because the covariance is going to be 0 when the variables are independent. Okay, please take note. Now let me quickly walk you into an example. If x and y are random variables with variances, you have the variance of x to be 2, variance of y to be 4, and they give you the covariance. Find the variance of the random variable z equal 3x minus 4y plus 8. Okay, now if you take a look at what you are seeing, okay, because you have been told, they gave you the covariance to be that guy. Okay, now look at the way I work things out. 3x, what is the variance of 3x? Oh, 3 squared variance of x, that would be 9. And what was the variance of x given? 2. That was why you see 9 times 2. Plus, how do I get, I'm trying to explain right now. How, give me 1 second. Oh my God, give me 1 second. How do we get this guy out? That's what I'm explaining now. Okay, now negative 4y. What is the variance of negative 4y? Negative 4 squared, 16, right? Variance of y. That will be, that's why you see 16. What is the variance of y? They give you 4. Does that make sense? Okay, now the next thing is you've been given the covariance, and if you take a look at the 8 is a constant, we don't need it. It's a constant. Now, the covariance that we occur is going to be between 3x and minus 4y. Now, you know what you're going to do now? Okay, which I need you to pay attention. I want to get the covariance. I want to get the covariance of, okay, 3x, right? The covariance of 3x minus 4y. I can ignore the constant 8. Okay, now you know what I'm going to do. You remember a formula that we normally write. That formula is going to say 2 covariance, right? 2 covariance. What am I going to do? I 4 do 3 times minus 4. What is 3 times minus 4? Minus 12, right? Minus 12 times 2. That 2 exists. Remember 2 covariance? That will be negative 24. Okay? That is why you have this negative 24 here. You see that now? You got a negative 24 by multiplying this by this. Okay? By multiplying, oh, sorry, that's a comma here. By multiplying this by this. Okay? Because from the law of covariance, okay, this guy here is basically going to be 3. You're going to have 3 into negative 4. Okay? 3 into negative 4. Okay? Then you're going to have the okay, the of xy. Okay, the of x comma y. But don't forget, you will always multiply that constant by 2. Okay, 3 times negative 4 is negative 12 times 2. Because two measurements are involved. That would be negative 24. Then what is the covariance giving negative 2? And that was what you did to get 130. Is there any question? Go ahead. You always multiply by what? Oh, no, not the absolute value of the covariance. You know, the covariance given was negative 2, right? Now, what is the coefficient of x? 3 in the equation. What is the coefficient of y? Negative 4. What is 3 times negative 4? Negative 12. Okay, that is a negative 12 now times 2. You see now, right? That will be negative 24. Okay, that makes sense, right? Okay, now that's how that guy goes. We'll go to the next one. Now that we understand the expectation of the products, we can now look at the covariance. Let me quickly tell you this. Because now what I'm trying to show you now, this is the formula for covariance in discrete and in continuous. But you know what? I quickly want to move to show you this. Do you see that guy? Covariance equal expectation of the product minus the product of the respective mean. You can see the reason why we need the expectation of a product, because in covariance, okay, we actually have expectation of a product. So take a look at all of that. Okay, of course, you know how to find mu of s, mu of y. Now, when I take you back to the table the other time, okay, you know how to find the mean. I've walked you through how to find the mean of x, the mean of y, and you know how to find the expectation of the product. Then you are set to find the covariance. Okay, the covariance will be super easy. Okay, so what I'm trying to tell you now is covariance. Okay, the covariance xy is expectation of xy of the product minus expectation of x and expectation of y. But in a situation where X and Y are independent, you know what happened? If X and Y are independent, you know this guy is going to be equal to this guy, right? When they are equal, what happens to covariance? Covariance is going to become 0. Please take note. That is if X and Y are independent. If they are not, the covariance will not be equal to 0. Okay, now from that, now we got a covariance of -9/56. Do you know from here, as I got the covariance of negative that, okay, this is going to, the covariance here can tell us the direction. -9/56, the direction is negative, that is what it's telling us. But the covariance does not have a statistical power to tell us the strength of the relationship. If I really want to know the strength of the relationship, that I need to standardize the covariance. How do I standardize the covariance? I actually need a correlation. Okay, now I'm going to write something now. Okay, the correlation now is basically a correlation. Okay, the correlation of xy is going to be covariance xy divided by the square root of the variance of x, the variance of y. You see? You see now? You see now? Which means no expectation of the product, no covariance, and without covariance, you cannot have a correlation. Can you see now? Okay, now, so take a look at all of that. Now, in a continuous case, look at another example here. We're given f of xy. Okay, of course, you can get f of x, you can get f of y, you can get the mean of x, you can get the mean of y, you can get the expectation of the product, you can get the covariance out. Okay, if you take a look at what you're seeing now, you are giving this guy a joint. From a joint, you get the marginal distribution of x, you get the marginal distribution of y. Then from there, you get the marginal mean for x, the marginal mean for y. Then from there, you get the expectation of the product. Then from there, you get the covariance. You can also get the variance, because you need, if you want to get a correlation, of course, if you want to get the variance, okay, you know the formula of the variance, right? You know the formula of the variance, right? Okay, the formula of the variance. Give me 1 second. The formula of the variance of x that I call sigma square x is expected value of x squared minus expected value of x all squared, and the variance of y, that is sigma square y, is expected value of y squared minus expected value of y all squared. Please take notes. Okay, so that's exactly what I'm trying to do, or here. Look at this. Now, from here, look at where I started. After I've added the covariance to be 4/225, I can go ahead and get the expected value of x squared, expected value of y squared, so that I will be able to get the variance of s. I will be able to get the variance of y. Finally, then I will obtain the correlation. Look at that. Okay, I will advise that you actually go through all of that. Oh, I put an exercise here. Okay, take a look at this exercise. This is a multivariate function, x, y, and z. Okay, I said find the values of k. What are you going to do to find the values of k? You need 3 integrals, right? 3 integrals. You're going to equate it to 1. You integrate and you solve for k. Okay, don't forget, that's what you're going to do here. Okay, now find the marginal distribution of x, y, and z. If I want to find the marginal distribution of x, okay, what am I going to do? Okay, go ahead. Exactly. Send me a message for extra credit. I'm gonna integrate with the variable. That's the variable I'm not interested in. If I want to get the f of x, I will integrate out with respect to y and z, just like what you said. Okay. I can also, what if I want to get the joint marginal? There's also what we call joint marginal. Okay. If I want to get the f of xy, I will integrate the out with respect to z, the variable I'm not interested in. Okay. Oh my God. We also have the expectation of the product when you got to 3 variables. How can you figure this out? Try that. Expected value of x, y, z. That should give you how many integrals are you going to have? 3 integrals. X, Y, Z. This guy, f of x, f of y, f of z. Any question? This is where I'm going to stop today. Like I said, we're in the process of grading your midterm 2. I have not posted assignment 6. I deliberately delayed that. Because I want to slow down. Okay. To those who have, if you have missed 1 or 2 assignments, send me a message. I can give you makeup. According to the syllabus, I propose 6 assignments, but I'm only going to use 5 assignments. 5. I will drop assignment with the lowest score. And for those of you, if you are satisfied with 5 assignments so far, like you are okay with your grade, you don't need to compute assignment 6 that I'm going to post tomorrow. Does that make sense? If you know that, oh, I'm satisfied with what I've done so far. I've done assignment 5. I don't need assignment 6. But you only need assignment 6. Maybe you want to improve on your grade, like because I'm going to automatically drop assignment with the lowest score. I want to announce once again, I slowed down. I've not posted assignment 6. That was deliberate. But I want to slow down. Okay. It's going to be posted tomorrow. The deadline is not going to be on Sunday. Okay. Because it's going to be the last assignment. And I using this opportunity, those of you who joined this class lately, if you joined this class very late and you miss 1 or 2 assignments, why can't you reach out to me for makeup? I'm flexible, highly approachable. Okay, make sure you stay safe and have a lovely day. Bye for
Wait,
now,
to
everyone.
clarify, right? I had a quick question. So you have, so of the 5 assignments that we've already done, one of them will
Yeah?
get dropped, or do you have to do 6 assignments for one of
No,
them to get dropped?
no. Before one assignment can be dropped, you have to do 6 assignments. Does that make
Okay.
sense?
Yeah.
But if you are satisfied with 5 assignments you've done so far, you may decide not to go for the 6th one. Does that make sense?
Yeah.
Okay. Have I answered your question, right?
Yeah. Yeah.
Okay.